the Hubble Space Telescope in operation for over 34 years has proven to be an extraordinary asset not only for astronomers but also for the curious minds of space enthusiasts around the globe. Although it was not originally intended to observe objects within our solar system, Hubble has captured numerous extraordinary phenomena that would have otherwise remained unnoticed. Many of the planets and celestial bodies in our cosmic neighborhood still lack dedicated missions, leaving large areas unexplored. In this vacuum of direct observation, Hubble's precision and stability have allowed it to become an indispensable eye in the sky, revealing the hidden dynamics and complexities of our solar system. Beginning close to home, one might assume the moon would be a frequent subject of Hubble's gaze. However, due to its large apparent size in the sky, the moon cannot be imaged in full by Hubble. Other missions, such as NASA's Lunar Reconnaissance Orbiter, provide far more practical imaging of the lunar surface. Even so, Hubble has played a key role in lunar-related experiments, such as during the 2012 transit of Venus across the Sun. Although the event did not directly involve the moon, scientists cleverly used the moon as a reflective surface to observe the event indirectly. Analyzing the sunlight that had scattered through Venus's atmosphere and reflected off the moon, they were able to test a method for detecting atmospheric compositions, an approach that has become fundamental in studying exoplanets. This technique of analyzing how light changes as it passes through or reflects off an atmosphere has since become crucial in our understanding of planets far beyond the solar system. Unlike the moon, Mars is a much more suitable target for Hubble's instruments. Hubble has repeatedly observed the red planet, capturing stunning global images of its surface, something not always possible for orbiters around Mars, which typically view only narrow swaths at a time. The images have proven immensely valuable, offering insights into Martian weather patterns, seasonal changes, dust storms, and atmospheric dynamics. A particularly striking series of images captured by Hubble was a time-lapse showing a global dust storm engulfing the entire planet, rendering the surface completely invisible. Against this backdrop, Mars' two small moons, Phobos and Deimos, can be seen darting around the planet. Hubble also captured a separate time-lapse of Phobos over a short 22-minute span, emphasizing how swiftly the moon orbits Mars, completing a full orbit in just 7.5 hours. This, in fact, the only moon in the solar system that orbits faster than the planet's rotation. These types of observations are not just visually compelling but also critical for mission planning, as future rovers and human explorers will need to navigate and survive in these volatile environments. As our gaze travels beyond Mars, we enter the asteroid belt, a turbulent region brimming with millions of celestial fragments. One such object that caught Hubble's attention in 2019 is asteroid 6478G. Despite its asteroid classification, Gault displayed twin tails resembling those of a comet, prompting scientists to investigate further. They discovered that the cause of these tails likely lies in the Yarovsky-O'Keefe-Radzivsky-Paddock-Yorpy effect, a phenomenon in which uneven solar radiation causes an object to spin faster over time. It, approximately 3.5 kilometers wide, now completes a full rotation every 2 hours, close to the theoretical limit of what such a body can endure. This rapid spin generates strong centrifugal forces, which in turn eject loose surface material into space, forming the signature tails. Most asteroids like GT are not solid rocks but rather loosely bound rubble piles held together by weak gravity. Eventually G may disintegrate entirely. These findings emphasize the dynamic nature of the asteroid belt, which contains between 1 and 2 million asteroids over a kilometer in diameter, alongside countless smaller ones. Another fascinating example of the belt's unpredictability is P/2010 A2, which at first glance appeared to be a standard comet. However, closer inspection of its nucleus revealed something astonishing: an X-shaped debris pattern inconsistent with typical cometary activity. Scientists concluded that this was the aftermath of a high-velocity collision between two asteroids. The filamentary structure consisted of rubble ejected in multiple directions from the impact site. Some of this material was drawn back toward the center by weak gravitational forces, while other debris escaped into space. Events like these, although rare, offer direct evidence of the ongoing violent processes that continue to shape our solar system. Though most asteroids follow relatively stable circular orbits, those that stray can encounter powerful gravitational forces, especially from Jupiter, the solar system's dominant giant. Jupiter, referred to as the solar system's vacuum cleaner, exerts a gravitational pull so immense that it has been known to alter the paths of comets and asteroids alike. With a mass comprising nearly a third of all matter in the solar system outside the Sun, Jupiter's gravitational influence is profound. A vivid example of this occurred in 1994 when comet Shoemaker-Levy 9 drifted too close to the gas giant. The comet had actually been captured by Jupiter's gravity 2 decades earlier and was orbiting as a temporary satellite. Eventually, tidal forces became too strong and the comet was shredded into multiple fragments. When these fragments collided with Jupiter's atmosphere at speeds of 60 km/s, they created explosive impacts. One of the largest impact sites left a dark scar approximately 12,000 kilometers wide, nearly the size of Earth. The explosion produced temperatures exceeding 23,000 Kelvin and released energy equivalent to 6 million megatons of TNT, over 600 times the combined power of all nuclear weapons on Earth. These events offered the first direct observation of a planetary collision and demonstrated Jupiter's role in potentially shielding the inner planets from catastrophic impacts. Jupiter's influence extends beyond just gravity. Its magnetic field and radiation belts are responsible for some of the most spectacular auroras in the solar system. Unlike Earth's auroras, which are sporadic and tied to solar activity, Jupiter's auroras are continuous and hundreds of times more powerful. In 2016, during NASA's Juno mission, Hubble was tasked with monitoring Jupiter's auroras for an extended period. These observations revealed that the auroras are not solely driven by solar winds but also by internal mechanisms such as rotating magnetic fields and charged particles within Jupiter's magnetosphere. The unique processes result in persistent, brilliant lights that encircle the planet's poles, a phenomenon not seen anywhere else in the solar system. Jupiter's many moons, Europa stands out as one of the most intriguing and promising candidates in the search for extraterrestrial life. Covered in a shell of ice, Europa is believed to harbor a vast subsurface ocean kept liquid by tidal heating generated through gravitational interactions with Jupiter. While missions like Galileo and Voyager provided close-up images of the moon's surface, it was Hubble that made a game-changing discovery by detecting potential water vapor plumes erupting from Europa. These observations in ultraviolet light suggested that the moon's ocean may be venting material into space, offering a tantalizing opportunity to sample its subsurface waters without having to drill through km of ice. Furthermore, Hubble detected the presence of sodium chloride, ordinary table salt, on Europa's surface. This indicates that its ocean may be chemically similar to Earth's, increasing the likelihood that it could support microbial life or at least prebiotic chemistry. Moving further out into the solar system, Saturn remains a focal point for observation, especially after the Cassini mission concluded in 2017. Then, Hubble has stepped in to provide the only continuous monitoring of the gas giant. The telescope has captured stunning images of Saturn's atmosphere, including vast storms that span thousands of kilometers. These observations are essential not just for planetary science but also for understanding atmospheric dynamics in gas giants more broadly. Hubble's ability to track these changes over time helps refine models of how similar planets might behave around other stars. Beyond Saturn lie Uranus and Neptune, two ice giants that have largely been neglected since the brief Voyager 2 flybys in the 1980s. 2. Hubble has proven invaluable. Has monitored seasonal variations in the atmosphere of Uranus, capturing shifts in cloud patterns and storm activity. Hubble has also discovered Neptune's smallest known moon, Hippocamp, a tiny celestial body only about 34 kilometers wide. Its discovery was particularly surprising because of its proximity to Neptune's largest moon, Triton, which likely would have disrupted or absorbed such a small object over time. The findings help astronomers refine their understanding of how Neptune's moons formed and evolved, suggesting that the solar system's distant reaches are still dynamic and filled with surprises. Reflecting on all these achievements, it becomes clear that the Hubble Space Telescope has revolutionized our understanding of the solar system in ways its designers never anticipated. Over the past 3 decades, it has consistently pushed the boundaries of what is possible, delivering not only breathtaking images, but also critical data that fuel scientific discovery. With continued maintenance, Hubble may well continue to operate until 2040, possibly even outlasting the James Webb Space Telescope in terms of operational longevity. Its enduring legacy is a testament to human curiosity and ingenuity, reminding us that even as we look billions of light years into the past, there is still so much to discover in our own celestial backyard. The universe, as Hubble has shown us time and again, is far from static. It is alive with activity, complexity, and wonder, waiting patiently for the next observer to unravel its secrets. Extending beyond the outer edges of Neptune, the solar system continues into a vast, dimly lit expanse known as the Kuiper Belt, a region teeming with icy bodies and dwarf planets. Though the Hubble Space Telescope was never designed to probe these cold and distant regions in detail, its adaptability has enabled it to make groundbreaking contributions here as well. Among the most notable of Hubble's achievements is its role in the discovery and characterization of trans-Neptunian objects, including the most famous of them all, Pluto. While Pluto was first discovered in 1930, it remained a blurry point of light in even the most powerful ground-based telescopes for decades. Hubble transformed that limitation by capturing the most detailed images of Pluto ever taken from Earth's orbit prior to the arrival of the New Horizon spacecraft. These images, though pixelated by planetary imaging standards, revealed surface features such as large, bright, and dark regions that hinted at the complexity later confirmed by New Horizons in 2015. Additionally, Hubble discovered 4 of Pluto's 5 known moons, Nix, Hydra, Cararos, and Styxes, shedding light on the chaotic nature of Pluto's satellite system and helping NASA engineers plan the New Horizons flyby with extraordinary precision. Beyond Pluto, Hubble has turned its attention to other denizens of the Kuiper Belt, including Eris, Haumea, and make each a dwarf planet in its own right. Hubble helped determine the size and albedo reflectivity of these distant worlds, clarifying that Eris is nearly as large as Pluto and in some measurements, possibly even slightly larger. The discovery of such massive bodies led directly to the reclassification of Pluto in 2006 when the International Astronomical Union formally defined the term planet, relegating Pluto and its kin to the category of dwarf planets. Haumea, with its elongated shape and rapid rotation, and make with its methane-rich surface, are among the most enigmatic bodies in the Kuiper Belt, and Hubble's observations have been critical in shaping our understanding of their compositions and orbits. But Hubble's utility in the Kuiper Belt hasn't ended with merely imaging or identifying these objects. In 2014, it played a pivotal role in selecting the second target for the New Horizons mission, 2014 MU-69, later nicknamed Arrokoth. Hubble's incredibly sensitive instruments identified this tiny 36 kilometers long object hiding in the darkness beyond Pluto. Without Hubble, New Horizons would have flown into empty space after passing Pluto. Instead, it continued its mission, culminating in the historic 2019 flyby of Arrokoth, the most distant object ever visited by a spacecraft. Arrokoth's boy-lobed shape and reddish hue revealed vital clues about the early stages of planetary formation, indicating that it formed through the gentle accretion of smaller objects in the early solar system rather than catastrophic collisions. Hubble's precision and reach made this scientific milestone possible, further cementing its legacy in planetary science. The telescope's contribution, however, is not limited to objects alone. Hubble has also been instrumental in studying the environments in which these objects reside, including the solar wind and the heliosphere, the vast bubble created by the Sun's magnetic field that encompasses all the planets and extends well beyond Pluto. By observing how the solar wind interacts with planetary magnetospheres, especially in the outer solar system, Hubble has helped researchers understand the changing conditions that influence planetary atmospheres and the potential habitability of moons like Europa and Enceladus. For instance, observations of Saturn's moon Enceladus, though limited due to its small size and distance, complement data from the Cassini spacecraft by suggesting the presence of subsurface oceans that erupt through surface cracks as plumes of water vapor.